Building mega projects is not just about concrete and steel. It's about precision, logistics, and human determination in motion. The upper structure erection of the Quesanuma Bay crossing bridge at the Kagoshio area constitutes a key phase in the construction of the landmark bridge spanning Quesanuma Bay in Miyagi Prefecture, Japan. The methodical sequence of operations took place beginning in early May 2019 and progressed through main girder installation, free cantilever segment erection, lift and set operations, and closure block installation. In early May 2019, the work zone at the Kagoshio section of the Quesanuma Bay crossing bridge entered the upper structure erection phase. At this stage, the focus was on constructing the super-elevated girders and segments that would span between the towers and piers above the bay. The schedule began with the installation of the main girder. Following preparation of the substructure and access platforms, the main girder erection commenced, forming the backbone of the deck structure. Next, the erection of the free cantilever segments in the span blocks was taken in sequence. First, the free cantilever erection progressed from span blocks J3436, where the segments were launched and counterbalanced from the towers and piers. Then, the free cantilever erection moved to J3637, followed by J3334, and then to J3738. In each block, the erection method involved assembling segments on fixed supports, then advancing outward in a balanced free cantilever fashion from each support. Multiple segments were installed, and post-tensioning was applied as needed to integrate the segments into a continuous superstructure. Following these free cantilever erection sections, the lift and set operation took place between blocks J4142. Large prefabricated units were lifted by heavy-duty cranes or special lifting vessels and placed precisely onto the blocks. After that, the erection proceeded at spans J4243 and then the CC erection at J4344. The CC designation refers to cast-in-place closure concrete or continuous concrete link segments, which serve to tie the previously installed free cantilever segments into a continuous deck. These sections were critical in converting the deck from a series of individual spans into a monolithic structure capable of functioning as a unified bridge deck. Finally, the closure block lifting and installation was carried out at span J2324. The closure block is the final segment that completes the span and aligns the deck to the next section, thereby closing the free cantilever gap and enabling continuity of the deck. During this operation, the prefabricated block was hoisted and carefully aligned with the adjoining segments, then secured by post-tensioning and closure concrete. With the closure block in place, the upper structure at the Kagoshio section was functionally complete and ready for further finishing works, bearings installation, deck surfacing, and expansion joint installation. Throughout this sequence, the erection works were carried out under rigorous safety and quality control regimes. The choice of method combining free cantilever erection and lifting of large prefabricated blocks was adopted to minimize disruption to marine traffic below and to cope with the challenging site conditions over the bay, As documented in the time-lapse digest video, the sequence shows the gradual build-out of the superstructure from the towers outward and the precision placement of heavy blocks by crane and barge. In summary, the erecting of the upper structure at the Gogosho zone of the Quesanuma Bay Crossing Bridge was a carefully orchestrated process beginning with main girder installation, advancing through successive free cantilever segment erection, then lift and set operations, followed by the CC erection and closure block installation. Each stage contributed to transforming the skeletal supports into a continuous deck ready to carry traffic across the bay. This methodical progression reflects modern bridge construction best practice, utilizing prefabrication, balanced free cantilevering, and block lifting to maintain schedule, quality, and safety in a demanding marine environment. The XCMG XGC88000 crawler crane is a remarkable achievement in heavy lifting technology, representing China's largest and most powerful crawler crane. With an incredible lifting capacity of 4,000 tons, this machine demonstrates the engineering excellence and innovation of XCMG, one of the world's leading construction equipment manufacturers. It is designed for large-scale infrastructure, petrochemical, and power generation projects, where extreme lifting requirements are essential. This model features a combination of a 108-meter main boom and a 33-meter jib, providing exceptional reach and versatility for complex lifting operations. At a working radius of 29 meters, the XGC88000 is capable of handling a total rated lifting load of 1,685 tons, ensuring high performance even under challenging site conditions. The modular boom structure allows flexible configuration depending on the lifting task, while the crane's massive crawler tracks provide outstanding stability and load distribution on uneven ground. The XGC88000 is equipped with a dual-boom superlift system, which greatly enhances lifting capability and operational safety. Its sophisticated hydraulic system allows smooth, precise control, enabling the operator to perform delicate maneuvers with heavy loads. The crane's advanced control cabin offers a comfortable and ergonomic workspace with modern monitoring systems, ensuring both efficiency and operator safety. Another notable feature of the XGC88000 is its transport-friendly modular design. Despite its enormous size, the crane can be disassembled into transportable sections, allowing efficient movement between project sites. This feature makes it ideal for use in large-scale energy installations such as nuclear power plants, wind farms, and refinery construction. In operation, the XGC88000 stands as a symbol of strength, precision, and reliability. It not only reflects XCMG's technological progress, but also showcases China's growing capabilities in producing world-class heavy machinery. With its powerful performance and versatile configuration, the XCMG XGC88000 has become a vital asset for major engineering projects across the globe, setting new benchmarks in the crawler crane industry. At a large-scale marine construction site, the collaboration between XCMG and Liebherr crawler cranes demonstrated exceptional lifting capability and precision. In the first stage, 4 cranes jointly lifted a massive offshore structure, raising it 30 meters above the ground and horizontally translating at more than 200 meters. This remarkable synchronized operation showcased advanced control and coordination between the XCMG and Liebherr machines. In the second operation, a heavy structure weighing over 800 tons was lifted to a height of 100 meters, further proving the crane's superior performance and stability. Finally, the XCMG crane competed once again with the Demag 1250-ton crawler crane, marking another milestone in heavy lifting technology. The successful completion of these operations reflected the engineering strength, innovation, and teamwork required for modern offshore infrastructure projects. The preparation of the roadbed is a crucial first stage in the process of road widening. It begins with excavation and leveling of the existing ground to the required level according to the design specifications. Excavators and graders are used to remove unsuitable materials, shape the subgrade, and ensure proper slope and drainage. Once the excavation and leveling are completed, the surface is carefully checked for uniformity and accuracy of elevation. After that, compaction is carried out to strengthen the subgrade and provide a stable base for the following pavement layers. Heavy rollers or compactors are employed to compress the soil until it reaches 95% of the maximum dry density, ensuring adequate load-bearing capacity and long-term durability. The compaction process is done in layers, with moisture content properly controlled to achieve the desired density. This thorough preparation guarantees that the expanded roadway will have a firm and stable foundation capable of supporting increased traffic loads and preventing future settlement or deformation. In modern multi-story steel construction, extending the height of columns is unavoidable, and this is achieved through a process known as column splicing. A column splice is a structural connection that joins 2 shorter column sections to create a continuous member. Since columns cannot be fabricated or transported in extremely long lengths, they are delivered in manageable segments. Consequently, splicing is necessary to assemble these sections on site and to maintain the structural continuity of the building frame. To begin with, the purpose of a column splice is twofold. On one hand, it enables the extension of column length by connecting prefabricated segments. On the other hand, it ensures structural continuity by allowing the column to behave as if it were one continuous piece, rather than 2 separate elements. As a result, the column can reliably transfer vertical and lateral forces from upper floors to the foundations without any weak points. Therefore, splicing is not just a matter of convenience, but a critical structural requirement. When it comes to types of splices, several methods exist, including welded and bolted splices. However, in practical building construction, bolted splices are by far the most common for site assembly. This is because bolted connections are faster to install, easier to inspect, and less affected by weather or working conditions. In contrast, welded splices are typically performed in fabrication shops under controlled conditions, while site welding is usually avoided due to quality and safety concerns. Thus, bolted splices have become the preferred solution in most high-rise projects. In a bolted splice connection, the assembly is achieved through the use of steel plates and high-strength bolts. Specifically, flange plates are attached to the flanges of the column sections, transferring axial and bending forces. At the same time, splice plates or web cover plates are connected to the web of the column, allowing shear forces to be transferred effectively. In this way, the combination of plates and bolts ensures that all types of forces, axial, shear, and bending, are safely transmitted across the splice. Moreover, the tightening of bolts provides sufficient clamping action, which improves friction between plates and further increases the load-carrying capacity of the joint. In addition, the design of a bolted splice must carefully consider load transfer. The splice is required to handle not only the axial load from the building weight but also bending moments caused by wind or lateral actions, as well as shear forces arising from floor slabs. For this reason, engineers must calculate bolt sizes, plate thicknesses, and spacing precisely to guarantee safety. Furthermore, the location of the splice plays an important role. Splices are ideally positioned near floor levels, where beams and slabs provide lateral restraint. This placement reduces the bending moment at the splice itself and enhances the overall stability of the frame. Equally important is the consideration of seismic design. In earthquake-prone regions, column splices must meet strict requirements to ensure that the building can withstand seismic forces without failure. For example, design codes may require a minimum shear capacity or compact detailing of the connected members. Additionally, bolted splices must be detailed to allow ductile behavior so that the structure can dissipate seismic energy rather than fail suddenly. Therefore, the detailing of splices is not merely a technical formality, but a crucial part of ensuring resilience during extreme events. Moreover, bolted splices offer several practical advantages during construction. They allow for rapid assembly of steel frames, which reduces construction time and labor costs. Because bolts can be pre-installed in the plates before lifting, site workers only need to align the column sections and tighten the bolts. This efficiency makes bolted splices highly suitable for tall buildings where large numbers of connections must be completed quickly. Additionally, inspection is straightforward since bolted joints can be visually checked, and torque tests can verify the correct tightening of bolts. Consequently, quality assurance is much simpler compared to welded joints. Nevertheless, it is worth noting that proper workmanship is essential. If bolts are not tightened correctly, or if plates are misaligned, the load transfer may be compromised. Therefore, site supervision and inspection remain critical to ensure that the designed performance of the splice is achieved in practice. In conclusion, column splicing is a fundamental process in multi-story steel building construction, and among the various methods, bolted splices stand out as the most practical and efficient solution for on-site assembly. By using flange plates, web plates, and splice plates secured with high-strength bolts, engineers ensure the safe transfer of axial, bending, and shear forces between column sections. Moreover, by carefully considering load transfer, location, and seismic requirements, bolted splices provide both structural integrity and construction efficiency. Ultimately, these connections make it possible for steel columns to rise seamlessly across multiple stories, creating the stable frameworks upon which modern buildings depend. The process of constructing a diaphragm wall begins with boring, which is the most critical and time-consuming stage. A trench is excavated in the ground using specialized hydraulic grabs or trench cutters, guided by a bentonite slurry that stabilizes the soil and prevents collapse. The excavation progresses in panels, typically several meters long, to the required depth, which may reach dozens of meters depending on design. The slurry is continuously circulated to remove excavated material while maintaining trench stability. During boring, Depth and verticality are carefully monitored with instruments to ensure the accuracy of the trench. Any deviation is corrected immediately to avoid structural issues later. Once the required depth is reached, the trench is cleaned using a desanding unit to remove suspended solids and ensure a clean surface for the next stages. After boring, reinforcement cages are prefabricated and lowered into the trench by cranes. These cages are carefully aligned and connected when deeper or longer cages are required. Proper spacing is ensured to allow concrete flow. Next, stop ends are installed at the trench ends to shape construction joints between panels. These elements, usually made of steel or PVC, define panel boundaries and allow sequential excavation and concreting. N. Finally, concreting is carried out using the Tremy method. Tremy pipes are inserted to the bottom of the trench, and concrete is poured continuously under slurry to avoid segregation. As concrete rises, slurry is displaced and collected for reuse. This ensures a dense, homogeneous wall panel with strong structural integrity. The Honam High-Speed Railway, one of South Korea's major infrastructure projects, demonstrates the nation's advanced bridge construction technology through the adoption of the Precast segmental method. This technique, applied in the construction of the Mangyang River Bridge within Section 3-3 of the project, represents a highly efficient and precise approach to building railway viaducts for high-speed trains. The system is characterized by the factory production of pre-stressed concrete box girders, each 25 meters long, which are then transported and installed at the site using specialized lifting and launching equipment. The PSM technique ensures the highest possible construction quality through complete industrialization and mechanization of the process. In traditional bridge construction, concrete casting and curing are performed on-site, exposing the structure to environmental variables such as humidity, temperature fluctuations, and uneven curing conditions. In contrast, the PSM approach allows each box girder to be fabricated in a controlled factory environment, where temperature, vibration, and concrete mix proportions are strictly monitored. This controlled process not only enhances structural strength and dimensional precision, but also minimizes human error and material waste, leading to superior performance and uniform quality. Each 25-meter box girder is a hollow rectangular beam designed to support both the track structure and the dynamic loads generated by high-speed trains. After fabrication, the girders undergo rigorous quality inspection and are stored in the yard until the site is ready for installation. Transportation is carried out using special multi-axle trailers capable of handling heavy loads over long distances without deformation. Once the girders arrive at the construction site, large gantry cranes or launching girders lift and position them accurately on the bridge piers, ensuring precise alignment and stability. The installation sequence is meticulously planned to guarantee both safety and efficiency. Before the girders are placed, the bridge piers are constructed and aligned with millimeter-level accuracy. Temporary supports or bearings are installed on top of the piers to receive the incoming box girders. Once positioned, the girders are fine-tuned to meet the design alignment and level requirements. Subsequently, adjacent girders are connected using post-tensioning tendons, which compress the segments together to behave as a single continuous structure. This process minimizes crack formation and increases the bridge's ability to resist dynamic and fatigue loads produced by high-speed train operations. One of the most significant advantages of the PSM method is the drastic reduction in construction time. Because the production of girders in the factory can proceed simultaneously with foundation and pier construction on site, the overall project duration is substantially shortened. Furthermore, the on-site assembly process is less weather-dependent and requires minimal formwork and scaffolding, improving both safety and efficiency. The high degree of prefabrication also limits the need for manual labor at elevated heights, thereby enhancing worker safety and reducing potential risks. From an engineering perspective, the PSM system provides exceptional precision and quality assurance. The use of advanced equipment such as automated concrete batching systems, vibration-controlled curing chambers, and precision steel molds ensures consistent dimensional accuracy and a smooth surface finish for each segment. Moreover, the controlled pre-tensioning and post-tensioning processes significantly enhance structural durability, reducing the need for future maintenance. The mechanized erection process, employing synchronized gantry cranes and hydraulic lifting systems, enables precise placement without extensive falsework, making it especially suitable for long-span viaducts crossing rivers, roads, or populated areas. The PSM method also offers environmental advantages. Since most operations occur in the factory, noise, dust, and waste generation at the construction site are greatly reduced. The limited use of on-site concrete pouring helps prevent contamination of nearby waterways and minimizes the ecological footprint. Additionally, the reduced construction time and traffic interference contribute to lower carbon emissions and improved site safety. The successful construction of the Mangyong River Bridge under the Honam high-speed railway project underscores the effectiveness of adopting industrialized bridge construction technologies. By combining precision engineering, advanced materials, and automated processes, the PSM method delivers bridge structures that are not only strong and durable, but also aesthetically refined, environmentally sustainable, and optimized for high-speed performance. This achievement represents a milestone in South Korea's continuous pursuit of efficiency